Hello, my name is Connor Dolan, and I'm going to run through the practical of day 5 in the International Boulder course. That was the practical is on multivariate twin modeling, the common pathway model, and the independent pathway model. I'm working from the workbook, which you have in your possession. I'll just show you that briefly. So this is the workbook. And what we're going to do is, in working through the workbook, we're going to cut and paste our code from the workbook into RStudio, run the code, and answer questions that pop up along the way in the workbook. First data set we're going to consider are the skinfold data. So these are skinfold measures at 4 positions on the body. And we've measured these in MZ and DZ twins, 214 MZ and 181 DZ twins. As I mentioned, the practical works as follows. You cut, paste code, run the code, look at the output, answer questions about the output. We're going to use Omx scripts. I'm not going to discuss the syntax in any detail, but the scripts are annotated in the appendix of the workbook document. Okay, so cut and paste the first bit of code shown here in the script window. That's top left, and at the bottom you can see the output. Before I start this, I set the working directory. I've already done that, but this is the way you do it, and you direct the RStudio program to your directory containing the data sets. Okay, so what we've done in this code is we've read the skinfold data, and then I've printed the column names in that data set. Yeah, so that's just to make sure that the column names are correct. And you can see it in the output window at the bottom. I'll just run the code. I've already done that, as you can see, but I'll do it again. So you can see that the column names, the variable names are shown at the bottom of the output window, and it includes family number, FAN, 2 measures of zygosity, SIG and SIG2. You can see BMI, BIC, SSC, SIL, and TRI. Are the phenotypes. T1, T2 stands for twin 1, twin 2. In the output, in the workbook, these phenotypes are described. Okay. Second step is cut and paste the next bit of code, and that is code to create the MZ and the DZ data frames separately. Yeah, so if you look at the code, you can see I'm using first defining the variables that I want to keep in this analysis. That's the 4 skinfold plus zygosity and sex. And I'm creating an MZ skinfold, DZ skinfold data frame. The last 2 lines are to obtain the descriptives of the data. Okay, so at this point, we've got the descriptives, and it's worthwhile to take a look at the descriptives because it's giving you the mean and the standard deviation and the sample size. And you'll note that the sample size nominally is 214 MZ twin pairs and 181 DZ twin pairs. But you can see from the N, the sample sizes associated with each phenotype, that there's a little bit of missing data in this data file because the sample size is 214. But when you look at try underscore twin 2, you can see it's 213, meaning that one of the values of triceps in twin 2 is missing. And the same applies to the DZs 181, except SIL and SSC in twin 2 both have one missing data. So we know that this data includes that these data frames include missing data. Okay, the next thing we're going to do is we're going to calculate, based on the data frames, the correlation matrix in the M sets and the D sets, and the covariance matrix in the M sets and the D sets. So again, cut and paste, run the code. And in the output window, you will see the covariance matrix, the correlation matrix, covariance matrix, correlation matrix. Yeah, the correlation matrix is easy to recognize because it has ones on the diagonal. In the workbook, I also include the output we see here in the output window. Yeah, so you can check what you see here should be exactly the same as what you see in the workbook. And this brings us to question 1. Check out the MZ and DZ phenotypic correlations of each phenotype and apply the rule of thumb. The rule of thumb is if 2 times the DZ correlation is greater than the MZ correlation of a given phenotype, we choose the ACE model as a point of departure in OpenMX modeling. But if 2 times the DZ correlation is smaller than the MZ correlation, you choose the ADE model. So what are the correlations and what model would you choose? Okay, so what we're referring to is the correlation. You look at the correlation matrix in the MZs and the DZs. And let's take an example. For instance, biceps twin 1, biceps twin 2 in the MZs. That correlation, that is in row 5, column 1, that correlation is equal to 0.78. And the corresponding correlation in the DZ matrix is 0.324. Yeah. So you can see that 2 times the DZ correlation is smaller than the MZ correlation. So with respect to phenotype, one would say this is probably an ADE model. Actually, this holds for all 4 phenotypes. All 4 phenotypes, the correlations associated with all 4 phenotypes suggest ADE model. Okay, that is the answer to question 1. Question 2 is use Falconer's equations. Using Falconer's equations, we can obtain preliminary estimates of the standardized ADE components. Okay, so the formulas, Falconer's equations, are shown in the question. And the idea is to apply these formulas to the 4 correlations, twin 1, twin 2 correlations, MZs and EZs, and then obtain estimates, preliminary rough estimates of the standardized ADE variance components. We're only going to do this for A and D. And the question is, apply these to the correlations, obtain the standardized components. How much of the phenotypic variance is due to A? Okay, well, if you do the sum, you'll find that the standardized A variance components are 0.509, 0.280, 0.377, and 0.329. So in percentages, additive genetic influences account for about 50%, 28%, 37%, and about 33% of the phenotypic variance. Question 3. In the output, we see the 8x8 covariance matrix of the MZs and the correlation matrix of the MZs. We can express the covariance matrix as a function of the correlation matrix and the diagonal matrix containing standard deviations. Okay, the idea is this. I want you to see that you can calculate, you can express the covariance matrix as a function of the standard deviations and the correlation matrix. And in question 3.1, you can see what the formula is. It is the diagonal matrix containing the standard deviations times the correlation matrix times the matrix containing the standard deviations. And you run this just to establish, just to show that you can actually calculate the covariance matrix as a function of the standard deviations and the correlations. Yeah. So if you run this, you'll see that the covariance matrix, as you've calculated using this formula, is exactly the same as the covariance matrix we saw before. And the zeros in the output windows is just that is the covariance matrix we saw before minus the covariance matrix we just calculated is 0, meaning that they're identical. Okay, this is important because when you carry out a multivariate twin model, yeah, you will estimate A, D, and E covariance matrix. That's the model that you estimate. But when you represent the models in your paper or your article, you may want to represent it using standard deviations and correlations. Yeah, so there's a difference between how you fit the model and how you might want to present the model. Okay, the next issue is, should we take into account the effects of sex? So sex is included in the data frames, and sex is coded 0, 1, 0 for males and 1 for females. That might be a simplistic representation of sex, I don't know, in this case, but we're just going to keep it simple so that we have a single covariate with a 0, 1 values. So how before we go into open mixed modeling, I just want to explore the data and find out, should I include sex as a covariant? Skinfold data measured in adult subs, it could well be that there are sex differences in skinfold. And if there are, I'd like to take them into account. So what we're going to do is we're going to cut and paste the following code. It's what we're doing is we're regressing the 4 phenotypes on sex in the twin 1 members. Yeah, so these are twin 1 members, M sets and D sets. This is the original skinfold data frame, including M sets and D sets, and we're regressing the phenotypes on sex in all the twin 1 members. We're not making a distinction between M sets and D sets. Okay, so we run this, and once we run it, once we have run this code, we can take a look at, say, the R11 output. R11 output will tell us whether or not sex is a significant predictor. Yeah, so here's the output, and what we're interested in is the regression coefficient in the regression of biceps on sex coded 0, 1, and you can see the regression coefficient is equal to 1.859, and it appears to be significant. Yeah, I'm not going to go into formal statistical testing. I can see that sex explains about, at the bottom of the output, 6.1% of the variance. So I consider that quite a lot. Yeah, you can take a look at the other output for the other phenotypes, and the overall the conclusion is that sex is probably a predictor of skinfold, and therefore it's desirable to include sex as a covariate in subsequent modeling. Okay, question 1.4 is repeat the analysis in the twin 2 members. Yeah, so that's not a big deal. You already have the code for the twin 1 members. The code for the twin 2 members is simply calls for a revision of the code we just cut and pasted. So here it is. So what I've done is I've changed T1 into T2, and that's it. Yeah, you can carry out the analysis in the twin 2 members also. And if you extract from the output, yes, see the R code, the R squared, you can get an idea of how much of the variance is explained by sex. So shown at the bottom of this output window, you can see that the explained variances are about, so starting at the bottom, 0.061, so that's about 6%. And then moving on, 4.3%, 5.6%, 3.2%, values in twin 1 members, and the values in twin 2 members are 7.9, 6.3, 9.2, and 6.4. So sex is explaining a substantial amount of the phenotypic variance in the skinfold measures. I conclude that it's desirable to include sex in subsequent modeling. Okay, so what we're going to do next is we're going to switch to OpenMX modeling. And what I'm going to do is I'm going to estimate the covariance matrix in the M sets and the D sets while simultaneously correcting for sex. Yeah. At this point, you might say, well, we've just calculated the covariance matrix in the M sets and the D sets just above in the previous part of this practical. But now we're going to do it using OpenMX, and that is useful because it allows us to firstly include sex explicitly as a covariate. So I'm going to obtain estimates of the covariance matrix corrected for sex or conditional on sex. And also OpenMX allows me to estimate the covariance matrix in the M sets, D sets optimally, taking into account missing data. So this is not, I don't know whether you're familiar with these terms, but you can use pairwise deletion or listwise deletion in the case of missing data. This is full information, maximum likelihood estimation. That takes into account all the available data. It's optimal. Yeah, so we're taking into account missing data because we know that there are missing data, not a lot, but there's some. And we can explicitly include sex as a covariate. So those are the advantages of using OpenMX to calculate the covariance matrix in the M sets and the D sets. Okay, here we go. I cut and paste, highlight it, and run the model. And the model should run without problems. Okay, so I've programmed this such that at the end of the OpenMX, I immediately extract the information that I want to see. Correlation matrix is shown in the output window. Correlation matrix, covariance matrix, M sets, correlation matrix, covariance matrix in the D sets. This output is also shown in the workbook. So again, you could check whether all went well. Question 1.5. What are the M set and the D set correlations of the 4 phenotypes based on the OpenMX output? And why do they differ from those that we saw when we answered question 2? So the correlations are now, if you can take a look at if you take a look at biceps, twin 1, twin 2 in the M sets, that's the top correlation matrix in the output window, you can see the correlation is 0.77. The corresponding correlation in the D sets is equal to 0.309. Yeah, so that's the first pair of correlations to consider. If you look at them, you'll find that the values are 0.7. So these are the D set, 0.77, 0.79, 0.76, 0.80. And then in the D sets, 0.30, 0.26, 0.29, 0.29. Yeah. So these differ slightly from the ones that we saw when we answered question 2. Why do they differ? Because now we're correcting for sex. Okay, question 1.6. What do you conclude on the basis of the M set and the D set cross-trait, cross-twin correlation coefficients for biceps and triceps? Okay, I'm not going to try and point those values out on this screen. I'm going to stop this screen sharing and go to the workbook, because I've reproduced the part of the matrix that this question is about here in the workbook. So the M set cross-twin cross-trait correlation is shown here. So this is biceps in twin 1, biceps in twin 2, biceps in twin 1, and triceps in twin 2. Yeah, so that's cross-trait cross-twin correlation is 0.737. And in the D sets, so that's twin 1 biceps, twin 2 triceps, it's 0.25. Okay, the answer to this question is, what do we conclude if we just eyeball these results? Well, we can see that the MZ correlations, and both within a phenotype and across phenotypes, are about 0.7 in the M sets, and they're about 0.2 to 5.3 in the DZs. Yeah, so this tells me that there are likely to be genetic effects both on the variances and on the covariances of these two phenotypes. And the model of choice is going to be ADE, because all the DZ correlations times 2 are smaller than the MZ correlations. Okay, that's question 1.6, and that means I think there are I don't know how many questions, about 14 questions in this, so we're about halfway. Okay, the next thing we're going to do is we're going to apply Falconer's equations again, but now we're going to apply them to the correlations that we found using OpenMX. Yeah, so the code to do that, I'll cut and paste the code and comment on it briefly. So here's the cut, copy and paste. So the bit shown at the top here, this is the code, and you can see that I've written a small function to do the calculation. Okay, so if you're not familiar with an R function, ignore that. I'm just using, this is just convenience to do it using a function. You can do it on a one at a time, explicitly programming the formulas, Falcon's equations. We run this, we find that the standardized additive genetic variant components are about 0.46, 0.27, 0.04, and 0.038. So they're going to differ slightly from the ones we saw previously because we're now correcting for sex. Okay, that was question. That was no question. That was a preamble to fitting the 4-variate ADE model. Okay, so what we're going to do now is we're going to fit the ADE model, and I'm going to parameterize the covariance matrix sigma A. I'm going to parameterize the covariance matrix sigma A. Yeah, so that's a 4x4 additive genetic covariance matrix in the ADE 4-variate twin model. Yeah, so here you can see in this slide, taken from the PowerPoint, you can see the MZ and DZ expected covariance matrix. And it is composed of an sigma D, and sigma E part. And each sigma is 4x4. And I'm going to parameterize the sigma A using covariance matrix. Sorry, I'm going to parameterize the covariance matrix sigma A using A standard deviations, A correlations, A standard deviations. Yeah. So that's what we saw, that you can calculate, you can express the covariance matrix in that fashion, as we saw in one of the previous questions. Yeah, so that's shown here. VA, that is that's what I call sigma A in the OpenMX script, is calculated as SA times RA times the transpose of SA. SA is the matrix with the diagonal standard deviations on the diagonal. RA is the correlation matrix of A. Yeah. Okay, so that is the way I'm parameterizing the covariance matrix, and I'm going to return to this parameterization in a second. Included in the script is the starting values for this problem. Yeah, so those are shown. I've highlighted that part of the OpenMX script, and in the workbook I'm explaining how I arrive at these starting values. So I won't go into that now. You can study that for yourself. But this is OpenMX, and in OpenMX you have to include starting values of the parameters of interest. Okay, this question 1.7 has to do with the starting values. I'll skip that. You can study that for yourself and move straight on to fitting the ADE 4-variate twin model with the parameterization of sigma A, sigma D, sigma E, as I just explained, yeah, using standard deviations and correlation matrices. So I'll cut and paste that code, or copy and paste that code, and then run it. So what we do now, we're now actually fitting a 4-variate twin model to the skinfold data. And let's see. So highlighted at the top, in the top left window, is the code for this problem. Again, this code is annotated in the appendix. I'm not going to discuss the details of the Omx script here. And when we run it, it runs, and the first thing it does, it carries out a likelihood ratio test comparing the saturated model to the ADE model. Yeah, so again, both of these include sexless covariate. I'm not going to consider that here. I just want to know, does this model fit the data reasonably well? Yeah. So what we find is that the p-value is about 0.04, and the likelihood ratio test is about 59.3, 42 degrees of freedom. So this is not a perfect fit, but it's not bad either. Yeah, just based only on the likelihood ratio test. You know, just to be clear, normally speaking, you'd say my alpha 0.05, let's say, and you carry out the test, and if the p-value you see in the likelihood ratio test is smaller than the 0.05, you'd say this model doesn't fit the data. Yeah, the hypothesis that this is an ADE model is rejected. Okay, that's the way that's the way formal good null hypothesis testing would work. Okay, and you're probably familiar with that. But in this context of multivariate twin modeling, the likelihood ratio test and p-values for the overall goodness fit of the model is not very important. You know, the large models generally do not fit the data. That is a simple truth of multivariate twin modeling. So you shouldn't be upset about the fact that the p-value we see here, 0.04, is smaller than our alpha 0.05. It's not a good idea to bother about formal goodness fit testing in this context. Large models generally do not fit. Yeah, and large models in combination with large sample size definitely do not fit the data according to the formal null hypothesis test. Okay, so we'll run the ADE model. Let's see. The results of main interest are the covariance matrix of A, D, and E. Let's extract those results for A and take a look at the results. Okay, so that involves a copy and paste of this code. I'll run this code. So what am I doing? I'm extracting the sigma A from the output, and I'm extracting the correlation, the A correlation matrix and the A standard deviations from the output, and shown. I'll just print them so we can see what they look like. Okay, so in the output window, bottom left, you can see the VA is equal to sigma A, so that is the additive genetic covariance matrix. Under that, you can see the additive genetic covariance matrix standardized, that's the correlation, the additive genetic correlation matrix. And then under that, you can see the additive genetic standard deviations. Yeah. So just to make sure this is clear, the VA is the covariance matrix. So what is the covariance matrix of the first phenotype? What is the variance of the first phenotype? 4.852. Yeah, so I'm referring to element 1,1 in sigma A, which is called VA here. What's the standard deviation? Well, that is the square root of the 4.85. And that's the value you can see in the matrix SA underscore 2.20. Yeah, so at the bottom, position 1, 1. Yeah, so we have the variance, a variance of the first phenotype, the a standard deviation of the first phenotype. The RA is the additive genetic correlation matrix. So if I take VA underscore and I standardize it, I will get the RA, and I'll demonstrate that. Cov to core is a R function that standardizes a covariance matrix. So if I run that, what I will see is the correlation matrix RA. Yeah. So the parameterization here is standard matrix of standard deviations on the diagonal times the correlation matrix times the matrix of standard deviations gives us the covariance matrix. That's the way I've parameterized this in this ADE model. And this applies to A, as you can see here. It also applies to the D and the E covariance matrix. Okay, verify that the additive genetic covariance matrix is a function of the standard deviations and the correlations. We've just done that. Yeah, so that's just a question of, I'll show you the code. This is the code, all the code you need. What we're doing is expressing the covariance matrix as a function of the standard deviation and the correlations again. Okay. So what we're going to do next is we're going to extract part of the output. We will want the sigma A, sigma D, and sigma E, not of all four, but just of biceps and triceps. Yeah. So we're going to take a look at part of the multivariate output. Okay, I've extracted VA, VD, and VE, sigma A, sigma D, sigma E, for the first two phenotypes, biceps and triceps. Okay. Oops. Okay. In the workbook, I'll just stop my share for a second and go to the workbook. This is what I'm talking about. So this shows you the A, D, and E model for biceps and triceps. Yeah, on the figure on the left shows you the variances and the covariances. The figure on the right shows you the standard deviations and the correlations. Yeah, so the figure on the right, that's the way we actually fit this model. If you scroll down in the workbook, we can see again on the left standard deviation and the correlations, and then on the right the standardized results. So that is, these are the same, the correlations are the same, but the path coefficients are now not the standard deviations of A, they are the standardized standard deviations of A, standardized standard deviation of D, and standardized standard deviation of E. Yeah, that's shown in the figure bottom right. So what we want to do is I want to reproduce those results. And question 10, look at the values of sigma A, sigma D, sigma E, VA, VE, D, and VE, and they should approximately equal the values in figure slide 27.6. Yeah, so I'm referring to the figures we just saw. Okay, so we just saw the VA, VD, and VE. Output window, bottom left, you can see the sigma A, the VA, sigma D, VD, and the sigma E. Okay, use what what we're going to do is we're going to take the sigma A, sigma D and sigma E, and we're going to extract from these output objects, we're going to transpose them. So we're going to use that output to calculate the standard deviations and the correlations. Yes, so take the VA, use COV to core, apply it to the VA, and that will give you RA, the androgenetic correlation matrix. If you take the diagonals of VA, that is sigma A, yeah, take the diagonal elements, those are the variances, take the square roots of the variances, that will give you the standard deviations. And that's exactly what you see here. The results are also reproduced in the workbook. So what I'd like to do now is I'd like to calculate the standardized variance components. Yeah. So that is, I have a variance components, let's say of triceps or biceps, either one. We have A variance components, D variance components, E variance components. If you add those up, that gives you the expected phenotypic variance. If you divide the A component by the expected, that gives you the standardized variance component. Yeah. So I have a little question. Question 1.2 is about the standardization, and I'll just show you the code. So here we have the code. We're creating the VPH is the expected phenotypic covariance matrix, and I'm dividing sigma A, sigma D, and sigma E by the total expected phenotypic covariance matrix. Yeah. Let's do that, and then I'm taking the diagonal elements. And these diagonal elements are the standardized variance components. And these standardized variance components, if I take the square root of these, those give me the path coefficients. Yeah, so the results you see at the bottom of the slide should resemble, hopefully, the results you see in figure 26, slide right. Yeah, so this what you see is in this slide, you can see the unstandardized solution, yeah, top left, the solution based on standard deviations and correlations, and then this figure on the left is the solution based on correlations and standard deviations, and then the figure on the right is the solution based on standardized variance components, standardized standard deviations and correlations. Yeah, and arguably the figure on the right here, this figure on the right, that's the easiest to interpret. Yeah, because if I ask you, what is the heritability, what's the narrow sense heritability of biceps, you can read it off from the figure, it's 0.37. So immediately you know 37% of the variance is attributable to adiabatic effects. Okay. The standardization is also shown at the bottom of the slide, as you can see here. So what we're doing here at the bottom of the slide is what we just did in RStudio. Okay, so let's continue. This was an exercise in how to represent the results. So question 11 is about reproducing figure 26, slide 26, right? But the figure we just looked at. Yeah. Question 1.12 is also about reproducing the figures that we just saw. So all this questions 11, 12, that's about we fit a model, multivariate model. How should we represent that in a path diagram? Yeah, using variances and covariances, using standard deviations, correlations, or using standardized standard deviations and correlations. Okay. Okay. Question 1.3 is, if I tell you that in the model, the environmental correlation equals 0.78, does that mean that E is contributing greatly to the phenotypic correlation? Okay, let me, I'd like to share my screen. So this is the question 1.3. The environmental correlation is about 0.8, 0.789. If I tell you the E correlation, the correlation between E is about 0.80, does that mean that E is contributing greatly to the phenotypic correlation between the two phenotypes? Now let's answer that question explicitly with respect to the path diagram shown here. Okay, so we're looking at the path diagram, standardized solution, that's the bottom right, sorry, the path diagram on the right. Okay, so the E correlation is 0.78. So that's almost 0.80. So that seems large. Okay, does that mean that E is contributing greatly to the phenotypic covariance between biceps and triceps? The answer is not necessarily, because the contribution of E to the covariance depends on the correlation, yes, the 0.787, but it also depends on the standardized path coefficients. Yeah, so these are the square root of 0.214 and the square root of 0.187. Yeah, so to derive the contribution of E to the phenotypic covariance, you have to take into account three parameters: the path coefficient from biceps to EB, the correlation between EB and ET, and then the path coefficients from ET to biceps. If the path coefficients are very small, then E will not contribute greatly to the covariance, even if the E correlation is 1. Yeah. So that is the that's explained in a little bit more detail in the workbook. Okay, we're almost finished with part 1 of this practical. Question 1.14 is, what is wrong with the 4x4 correlation matrix of D? Okay, so we can extract that from the output, and I'll show you how to do that. Cut and paste the code. So I've extracted the RD, R_D. Sorry, RD underscore is what I've called it, RD underscore. What does that look like? Here it is. Okay, so at the bottom of the screen. And the question is, what is wrong with this correlation matrix? Yeah. So if you eyeball it, you can see that some of the correlations are slightly larger than 1. Okay, and that's just what the problem is here, that the correlation should lie between -1 and +1. Those are the bounds. Yeah. And we find that some of the correlations are slightly larger than 1. So is that a problem? It's not a problem in this context, because some of them are larger than 1, but only slightly larger than 1. So the conclusion, my idea would be that the correlations are actually equal to 1. Yeah, I've not bounded them when I estimated them. I didn't impose any constraint. So the true values are 1, but the values in the sample are slightly larger or slightly smaller than 1. You know, that's my idea. That's what I think is generating these data. Yeah. So what we're going to do is we're going to test the hypothesis that they're all equal to 1. So in the workbook, question 1.5 is use Omx set parameters to fix the decorrelations to 1, and then use Mx compare to carry out the test of the hypothesis that the correlations are all equal to 1. Yeah. So I'll show you, I'll copy and paste the relevant code. Okay, so the first function is Omx set parameters. That is an OpenMX function that allows me to fix given parameters in a model to given values of my choice. Yeah, so the correlations in the D matrix are called RD21, RD31, RD41, RD32, RD42, and RD43. Yes, I'm going to take those parameters, I'm going to fix them to 1 and say that they're no longer free parameters. So I want them to be fixed to 1 and rerun the model. Yeah. So effectively, I'm imposing the constraint that the correlation matrix of the dominance effects all contain values 1, perfectly correlated dominant effects over the 4 phenotypes. And then the MX compare shown here at the bottom, that's the likelihood ratio test. And we'll see, we'll run this quickly. Okay, we can see that the likelihood ratio test statistic is 2.68. The degrees of freedom are equal to 6, and the p-value is large. It's nowhere near my so-called, let's make the alpha 0.01. Well, the p-value is 0.84. So there's no reason to reject the hypothesis that the correlations are indeed equal to 1. Why are the degrees of freedom equal to 6? Because I fixed, the previous model had 6 D parameters that were freely estimated. The revised model has 6 D parameters that are all fixed to 1. Yeah, so effectively, I've removed 6 free parameters, turned them to fixed parameters I'm no longer estimating. The difference in the number of free parameters in the previous model and in this model is 6, yeah, because I've fixed 6 correlations to equal 1. Okay, so what we conclude is that the correlations between the D effects are all equal to 1. And that means that there are no phenotype-specific dominance effects. There are dominance effects, but they are shared 100% by all 4 phenotypes. Okay, this concludes part 1 of the practical. Part 2 is about the skinfold data. Before I finish up, I want to say one thing about this parameterization. So what we've done is we've fitted an ADE model here, using in which we're estimating sigma A, sigma D, and sigma E, 4x4 covariance matrix A, D, and E. But I've modeled that, or parameterized that using standard deviations and correlations. Yeah. That's okay, because I was not interested in testing whether, say, sigma D is equal to 0 or not. I chose this parameterization explicitly because at the end of this practical, yeah, that is question 1.15, was about fixing the correlations to 1. And this parameterization is ideally suited to that end, because we can refer to the correlations explicitly, RD21, RD31, etc. Yeah. If you want to test whether sigma D is equal to 0, so can I reduce the ADE model to AE model? In that case, you would not use this parameterization. You'd estimate the sigma D covariance matrix without constraints, yeah, just as a covariance matrix, not parameterized using standard deviations and correlations. In part 2 of the practical, we'll be testing whether a given model, whether the model for neuroticism items is ADE versus AE. That is, can we drop the sigma D? And in that context, we will not be using this parameterization. We'll be using parameterization involving estimating the sigma D unconstrained as a covariance matrix. Okay, that concludes the first part of this practical.